Hi everybody, this video is designed to help you with the Chapter 16 Math Excel, the binomial distribution. Chapter 16 is all about different probability models. We mainly focused on the binomial distribution, but we looked at the geometric distribution a little bit too. I would highly encourage you reading through Chapter 16 a little bit, just as a review. I'm going to post a link along with this post. So let's get started on this Math Excel. This should only take about 10 minutes. It is generally believed that nearsightedness affects 10% of children in a certain region. The school district tests division of 150 incoming kindergarten children. How many would be expected to be nearsighted? And then we'll have to figure out what is the standard deviation for the number of nearsighted children in this group. So how many would we expect to be nearsighted is sort of like the expected value of this binomial distribution. And this is binomial because a child is either nearsighted or they're not nearsighted. Whenever it's one or the other like this can be modeled by a binomial probability. And here is all the relevant information you need to know about binomial probability right here. The mean of a binomial distribution is just n times p. So we know that there's 150 children that were sampled, and the probability of them being nearsighted is 10%. So we're just doing 150 times 0.10. And then we know that we would expect in that group 15 of them to be nearsighted. Check answer. Nice work. Yeah. So our next question is, what is the standard deviation? So we're going to use this formula right here, the square root of NPQ. Let me go ahead and type that into my calculator. The square root of 150 multiplied by P, which was 10%, multiplied by the complement of that Q, 90%. And we get 3.67. They want us to round it to 2 decimal places. 3.67. See what we got here. Good job. All right, next question. I'm going to keep these formulas up, but I'm going to make it a lot smaller. At a certain college, 4% of all students come from outside the country of that college. Incoming students there are assigned at random to freshman dorms where students live in residential clusters of 47 freshmen sharing a common lounge area. How many international students would you expect to find in a typical cluster? With what standard deviation? So 4% of all students come from outside the country. And if there are 47 freshmen sharing a common lounge area, how many would we expect to be international students? So we're just going to take n, which is the number of students that happen to be in that cluster, which is 47. And we're going to multiply that by 4%, the probability that a student is an international student. And we get 1.88. They want us to round it to 1 decimal place, so 1.9. And the standard deviation, square root of NPQ, 47 times 0.04 times 0.96. 1.3. Let's give that a try. All right. Next question. All right. So in this question, we're actually going to make use of this formula here, the choose function, and choose x, or as we call it in our class, NCR for the button on our calculator. So I think the way I presented it to you in class was NCR x multiplied by P to the X multiplied by Q to the N minus X, where N stood for the total number of trials, X was the number of successes, and P is the probability of a success, and Q is the probability of a failure. So, in this situation, a certain tennis player makes a successful first serve 75% of the time. So, our P is 75%. Assume that each serve is independent of the others. If she serves 9 times, what's the probability that she gets all 9 serves in, exactly 7 serves in, at least 7 serves in, and no more than 3 serves in? So if we're getting all 9 of them in, we have to assume that out of all 9 serves, she was successful 9 times. The probability of getting a serve in is 75%, and we're saying that that occurred 9 times. The probability of not getting a serve in is 25%, and we're saying that that didn't occur at all. So this is our calculation. We have to type into the calculator. 7 NCR, 9 NCR9 multiplied by 0.75 to the 9th power multiplied by 0.25 to the 0 power. And we get 0.075. They went 3 decimal places. All right. What's the probability that she gets 7 serves in? So it doesn't say which 7 she gets in. It could be the first 7, the last 7. It could be the first 2, then she misses 2, and then makes the next 5 in. So we have to consider every possible way that she can make 7 serves out of 9 serves. And that's exactly what this part of the function does. It counts every possible way you can select 7 things out of a group of 9 things. And the probability of getting 7 of them in, you just take the probability of getting 1 of them in and raise that to the 7th power. But if she makes 7 of her serves in, that means she's missing 2 serves. The probability of missing a serve is 25%, and that's happening 2 times. And these are all being multiplied by one another. I should throw some multiplication in there. So we have the same calculation as before, except we're going to change that 9 to a 7 and change this 9 to a 7. Change this 0 to a 2, and then what do we get? 0.300, and they want it 3 decimal places. All right. Get rid of that. What's the chance of her getting at least 7 serves in? So at least is a fancy way of saying 7 or more. That we have to consider the possibility of her getting 7 in, getting 8 in, or perhaps getting all 9 of them in. Well, we just figured out the probability of her getting 7 in. We figured out the probability of her getting all 9 in. If we figured out the probability of her getting 8 of those serves in, and then added up those 3 answers, that would give us our answer. So we're just going to go ahead and find the probability of her getting 8 of the 9 serves in by changing that to an 8 there, changing that to an 8, changing this to a 1. When you use this formula, the number here, let me highlight it. These two should always add up to this number here. Now I have to have my in my calculation, my exponent here and this exponent here always add up to this number here. So I can take these 3 answers and add them up, and that'll be the answer to this 3rd question. So just to review, the probability of getting at least 7 serves in is the probability of getting 7 serves in, the probability of getting 8 serves in, and the probability of getting 9 serves in, all added together. So I'm just going to go to my calculator and add these calculations. So I'm going to highlight them, plus this one, plus this one, and that should give us the probability, 0.601. All right. Now, there's another way we could have done that problem. The probability of getting at least 7 in is the complement of the probability of getting 6 or less in. And there is a button on the calculator that will calculate the probability of getting 6 or fewer serves in, and that is the Binomial Cdf. So if I wanted to, I could have done this differently. I could have done 1 minus the probability of getting 6 or less in. So I'm going to do Binomial Cdf on second bars to get into my distributions. Binomial Cdf. There was 9 serves that she took. Probability of making a serve in was 75%. I'm saying the probability of her making 6 or fewer in. And see how it gives us the exact same answer if this is the same as this? That's another way you can do that same problem. And we are going to use that here too. What is the probability that there are no more than 3 serves made? So no more than 3 is 3 or less, and that means the probability of her making 0 serves in, 1 serve in, 2 serves in, or 3 serves in. That's 4 different calculations we would have to add up, but luckily the button for it on the calculator makes it a lot easier. We're just going to make use of that Binomial Cdf. Going to set this to 9 serves she's taking in total. Probability of making a serve is 75%. And we have to calculate the probability of making no more than 3 serves in. So that's 3 or less. And that's exactly what this will give us. And that's 0.00999. They want us to round it to 3 decimal places. That would actually round to 0.010. So that 99 right there sort of rounds up to 100. So that's just going to be 0.010. Check answer. All right. One more question to go. A true-false test consists of 70 questions. How many does a student have to get right to convince you that he is not merely guessing? Explain. Well, in a true-false test, there is a 50% chance of guessing correctly. So I've used a typical expected value formula for the binomial distribution, n times p. You would have 70 multiplied by the probability of guessing it correctly is 50%, and you get 35. We'd expect that somebody would get around 35 questions correct simply by guessing alone. Now, how many questions would they have to answer correctly to convince us that they're not merely guessing? You can kind of think about that in terms of standard deviations. The standard deviation of a binomial distribution is the square root of NPQ. So the standard deviation in the number of correctly answered questions in this case, square root of NPQ is equal to 4.18. And we learned already that anything more than 3 standard deviations above the mean is exceptionally rare. And it would not occur strictly by chance. There's a very small likelihood of result 3 standard deviations away from the mean occurring strictly due to chance. So we're going to take our mean, 35, and we're going to add 3 standard deviations above the mean. 3 standard deviations. And that brings us up to 47.54. So if we round that to the nearest whole number, about 48 questions right. 48 questions correct would be 3 standard deviations above the mean, and it would be exceptionally rare to see that result from a student who is guessing. So if we look at all these answer choices, answer choice D says that the student would need to get about 48 right, at least 3 standard deviations more than the average student would get right just by guessing. This should be our answer. Let's try. Okay, this is a short video. I hope this helps you on this Math Excel. I'm going to continue to make a few more. Good luck. Ask me questions on Google Classroom or email. Thanks for watching.